In this video, we're going to be reviewing factorial notation. Factorial notation is a way of taking sequences and then writing them in a simplified condensed form. So in the example that we have in the first set here, we say, how can we describe the sequences of 5 times 4 times 3 times 2 times 1, or the product of all of these? What we can do is we can actually just write this as equal to 5 factorial, or an exclamation point next to it, and that means to expand it as a product of all the numbers below it to 1. And similarly, if we take the bigger sequence here starting at 7, this one's going to be equal to 7 factorial, which yet again just means take all the numbers that are below 7 and make them the product that go all the way down to 1. Now what about if we look at n plus 1 factorial or n minus 3 factorial? These types of sequences, they can actually go on to negative infinity, and they reduce the inner bracket by 1 each. So to write these ones out, we would say it's equal to n plus 1 in brackets times n minus 1 times ... We could go all the way down to some form of x value or infinity value. So you can see how we're just reducing the inner bracket by a digit of 1 and just keep reducing it. Similarly with the n minus 3 factorial, we go n minus 3, then we reduce it to n minus 4, reduce it one more time to n minus 5, and then it's going to be times. We can go all the way yet again to something like n minus x factorial as our final part of our sequence, but that would be to determine based on whatever sequence number we're given or what we're looking for in a given problem. So let's see how this works in an example. So we know that factorial notation, or the exclamation point next to a number, is going to expand these numbers. So what I can do is actually rewrite this form that we have here. So if we have in example 1, 3 factorial over 5 factorial, let's write that out in expanded form. So we have 3 times 2 times 1 all over 5 times 4 times 3 times 2 times 1. Now, what do we notice about when we expanded this factorial? The first thing I notice is that we have a 3 in the numerator and the denominator, a 2 and a 1 all in the denominator in the numerator. So what I can do is, if you recognize this right away, you can actually just cancel it. But in this case, I'm going to actually just group these together just so that we can see they're the same. And then if we know we're multiplying things in both top and the bottom, or the numerator and denominator, we can actually just cancel them from both. So I'm going to cancel it from the numerator here and cancel it from the denominator. And anything of itself, or anything the same over itself, is just equal to 1. So we get 1 over 5 times 4, because that's the only part left over, right? And then now we just have 1 over 5 times 4, which is just 20. So we can say that 3 factorial over 5 factorial is equivalent to this 1 over 20 when simplified. So on a quiz question, you may get something like, simplify this factorial, and you might have to write it in this simplified form like this, showing your steps that you can cancel this. Now let's take a look at another example here. This example is, instead, we have 2 things within the bracket next to our factorial or our explanation point. So what we want to do is we want to say, if we know that it's in decreasing order, in the cases where we have these brackets like this, it actually means that we can set it equal to, let's start in the numerator. So if we're decreasing in the brackets here, it's going to be n plus 1 bracket, and then we have n by itself we could stop anywhere here. We could technically stop here and just write a factorial, but what I'm going to do is just continue one more of decreasing. So I'm going to decrease it one more time to n minus 1 factorial. And then I'm just going to rewrite the denominator here as n minus 1 factorial. And yet again, do you see how we get the same thing of, we have 2 terms, one in the numerator and one in the denominator, that are the same? We have the 1 here and the 1 here. And so we can actually just cancel those out because they're being multiplied or divided in this case. And then we would say, what are we left with? Well, anything over itself is just 1, so the parts canceled just turn to 1. And we're just left with n plus 1 times n. And then this can also simplify too if we just FOIL or apply this n to both terms multiplied, we would get n squared plus n. And so our equivalent term of this n plus 1 over n minus 1 factorial is this bottom term here, simplified. Now these next two examples are just going to reinforce what we just learned above, just two more examples of the same kind of concept. So like we said, we take the number that's in front of the factorial or the exclamation point and we expand it all the way down to 1. So 7 is going to go 7 times 6 times 5 times 4, and then I'm just going to write dot 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 continued all the way down to 1. We don't have to write in the 3, 2, and that's so a thing. And then we can go over 10 times 9 times 8 times 7 times 6 times 5 times 4. But do you see how we're getting that repeating section here? So this would go down to down all the way to 1. We're going to get a repeat at that 7 point because 7 factorial is actually shown in the denominator here when we've expanded out that 10, so we can cancel this one here, and then we can cancel the one in the denominator, and then we're going to be left with anything over itself, which is 1, so we get 1 over 10 times 9 times 8. This is equal to 1 over 720. And that's equivalent to 7 factorial over 10 factorial. Okay, let's go to example 4 here. Example 4 is very similar to example 2. What we need to remember is that within the brackets, we're decreasing the term by 1 on both of these. So let's start in the numerator. The numerator, if we're going to decrease this, we can go n plus 1 times n minus 1 times n minus 2. Do you see how we're decreasing this? And then I can stop wherever I want. Technically in the sequence, I can just stop right here. And then because this is where I decide where to stop, it's because it replicates whatever in the denominator. So this is the whole goal of simplifying these, is we just need to find one term either in the numerator or denominator that we can cancel that's equivalent to both, and then whatever's left over is our answer. And then we just have to simplify it from there. So we have n minus 2 factorial in the denominator. Yet again, what we can do is we can say, hey, we have similar terms in the numerator and denominator. Let's just cancel those out. Anything over itself is just 1. And then we get n plus 1 times n minus 1 left over. And then let's try and simplify this for what we have. So we'll FOIL the first set of brackets. So we'll apply the n or multiply the n to the first two terms. That's going to give us n squared plus n. And we're going to keep that in brackets just because we're going to have to multiply it to this next set of brackets here. So now if we FOIL this one, starting with the first, we're going to have to apply the n squared to both the n and the n minus 1. So that's going to give us equal to n cubed minus n squared. Then we're going to have to multiply the n to both the other n and the n minus 1, which is going to give us plus n squared minus n. And then we should see how we have two of the same term right here. So those ones we can actually just technically cancel out. And then we're left with an answer of n cubed minus n. And that's going to be equivalent to our original term. Now for a little bit of more application base. Instead of just simplifying and getting a reduced term, what we're going to do is actually solve for that value of n in a given equation. So in this case, we're going to solve for n. What we're going to first have to do is simplify the left-hand side with those brackets. So we're going to take that n minus 5 factorial over n minus 7 factorial and simplify it. Remember, we're always reducing the inner bracket by 1 or reducing the number by 1. So in this case, it's the left-hand side becomes n minus 5 times n minus 6 times n minus 7. And I'm going to stop here with the factorial because do we see how we have an n minus 7 factorial that replicates our denominator? So I'm going to stop here, and then we say this is equal to 6. We know we have a term in both the denominator and the numerator that's the same, which is this n minus 7 factorial. So I'm just going to cancel that from both. And then I'm left with n minus 5 times n minus 6 is equal to 6. Because we maintain that right side, we're not going to do anything with it. Then we have to FOIL this left-hand side, so n times n and n minus 6. That's going to leave us with n squared minus 6n. Then we have to FOIL the 5 to the n and the 5 to the 6, which is going to give us minus 5n plus negative 5 times negative 6. That's going to give us plus 30. And then that's equal to 6. And then now we just need to simplify this negative 6 and negative 5n. So we're going to get n squared minus 11n plus 30 is equal to 6. And then now, in order to get an n value, or in order to factor, what we're going to have to do is set the right side equal to 0. So I'm going to move that 6 over. I'm going to subtract it from both sides. And then we're just going to continue the work up here to the right. So we're going to get n squared minus 11n. Well, if we take away a 6 from 30, then we're going to get plus 24. And we took away the 6 on the other side, or the right side, so that's just equal to 0. Now, in order to get an n value here, what we have to do is we have to say, this looks like a perfect trinomial, so what we're going to have to do is say, let's factor this, and then that should give us n values. So when we factor any problem, we say what multiplies, or I'm going to draw it here above, we're going to say what multiplies to make the outside terms. So we have multiplies to make 24, but then what adds to make the negative 11. In this case, what I'm going to say is I'm pretty sure that's going to be both negative 8 and negative 3. And let's just try that out for both slots here. Negative 8 times negative 3, yeah, a negative times a negative is a positive. And then we have 8 times 3, which is 24, so we're good there. Negative 8 plus a negative 3, yeah, that's 11, so I would say we're good. And then we don't have to apply decomposition because the value in front of n here, or in front of our squared term, that's just 1. And anytime that's 1, you don't have to do decomposition, and we can immediately rewrite this as factored terms by going n minus 8 and n minus 3 is equal to 0. And then what we can do to get our n values is say n minus 8 is equal to 0 and n minus 3 is equal to 0. By solving for n in each of these cases, we're just moving the numbers across. So we're going to go plus 8 to both sides and plus 3 to both sides. Thus, the two values of n we get are n is equal to 8 or n is equal to 3. And that is our final solution of the n values that satisfy this equation. Finally, let's take a look at the example where it's very similar to the last one, except we're looking for the largest value of n that satisfies the following. So in example 5, we got two solutions. So if we're faced with the same type of question, we would say, well, n is the largest value. It's the largest n value that applies and makes this equal, so that would be our solution. So we're going to do the same type of steps as we did in this problem, but now we're just going to replicate it and then only choose our largest value. So in this case, let's do the same thing that we did before. So remember, we're always reducing the inner bracket by 1 in these cases. So if I'm reducing the inner bracket, I'm actually not going to touch the top, but I'm going to work with the denominator on the left-hand side. So we're going to get n factorial over n plus 2 times n plus 1. Just keep reducing. N times n minus 1. But do you notice how we don't actually even need to go that far, because in our numerator, we have n factorial. So let's just stop when we get to n once we've reduced it there, and we'll just write factorial. And then this is equal to 1 over 6n. Okay, like the problems we had before, we see two things, one in the numerator, one in the denominator, both the same. So what we can do is we can actually just cancel those out. And then anything over itself is just 1, like we did in the previous problems. So we have 1 over n plus 2 times n plus 1, which is equal to 1 over 6n. And the nice thing is when we get a problem like this, we don't actually have to do anything other than just flip the fractions and make them the reciprocals, because the reciprocal is technically the same as this problem here. The values won't change. So I'm just gonna, we could either say, let's cross multiply, which would put each term in the opposite numerator, or we can just say, we know that that's what we're going to be doing, so let's just flip the fractions, put their reciprocals, and then that keeps our job simple. So we have n plus 2 times n plus 1, which is equal to 6n. And then remember, just like we did in the last problems, we have to apply the n to both, just like we're foiling. So we have n squared plus n. We're going to multiply 2 to the n and 2 to the 1. So that gives us plus 2n plus 2. And then this is equal to 6n still. Let's combine some of the terms we can do. So we have an n and a 2n. So that's going to be n squared plus 3n plus 2 is equal to 6n. And then like we did before, we're just going to move that one term on the right over. So we have minus 6n, minus 6n. And then let's continue the problem up to the right here. If we move that 6n from the right to the left, we have n squared minus 3n, because 3n minus 6n is going to give us a negative 3n. And then plus 2 is equal to 0. Now we're in the case scenario where we have to do our factoring in order to get our n values. So to factor this, we can say what multiplies to make the product of our outside numbers. So that's going to be equal to 2. And then what adds to make the middle term, which is negative 3. In this case, I'm going to say that that is going to be negative 1 and negative 2. Negative 1 and negative 2. And let's just reinforce that. So negative times a negative is a positive, and then 1 times 2 is 2. So we're good there. What about negative 1 plus a negative 2? Yeah, that's definitely negative 3. So I would give a big check mark there and say we're all set. Now we don't have to use decomposition, because like we had in the last problem, we only have a 1 in front of this n squared. So we can immediately write our factors. N minus 1 times n minus 2 is equal to 0. And then we set them both independently equal to 0. And then we have to add the numbers over, move them to the other side. Thus, we get n is equal to 1, or n is equal to 2. Now remember, this problem differed a little bit from the last one. The last one just said solve for the value of n, and in this case we had two values, n is equal to 8 and n is equal to 3. Those were both okay, we could both include them. But in this next problem, it says we need the largest value of n that satisfies the following. So to satisfy this equation at the beginning, we have to look at the largest value that does that. In this case, our answer is n is equal to 2, because that's the largest value for that n value that makes this statement true.